All right, so welcome back. We are going to go into our discussion on rotational motion and angular momentum. So let's go ahead and get started. First, we need to understand a little bit more about our angular motion in general. So the first idea here is going to be our angular acceleration, okay? And we need to recall what angular velocity is, okay, and its relation to linear velocity, okay? So take this circle here, and we have some rotation, and we want to know the angular velocity and its relation to linear velocity, and we talked about that in the past, but just kind of get you, kind of remind you guys of what that is. Okay, so our angular velocity, which is this omega here, is equal to our change in angle, okay, so this change in angle over our time, okay, so it's our change in angle over time, okay. Now when in the past we went ahead and related that to our linear velocity, so our linear velocity is our v here, and it equals to our radius times our omega, which is going to be our angular velocity. Okay, so we need to understand that before we can proceed. We need to remember that idea of this angular motion. Okay, so with angular velocity, if we have a change in angular velocity over a change in time, then we come up with angular acceleration, which is this alpha here, okay? So this is equal to angular acceleration, okay? And so again, remember in just a linear motion, we had that acceleration is some change in velocity over some change in time. So this makes sense for us to go ahead and have our angular acceleration now a change in our angular velocity over a change in time. Okay, so these are similar, as you can see. Okay, and just to point out, our units is now in radians over seconds squared. Okay, so that's what the RAD is, radians. Okay, and so now let me go ahead and give you guys some examples of calculating this acceleration. Okay, give me 1 second. Okay, so here is our first example here, example 10.1. We are supposing a teenager puts her bicycle on its back and starts the rear wheel spinning from rest to a final angular velocity of 250 RPM in 5 seconds. Okay, so let me go ahead and change this color. I'll get blue. Okay. And we want to calculate the angular acceleration in radians per second. Okay, so that's my part A here. Okay, so let's see. We have that our velocity, okay, changed from 0 to 250 RPM. So our velocity is going to be 250 RPM, okay, and our change in time is just our 5 seconds, okay. Now, let me make this a little bit thicker. I feel like it's a little too thick or thin. Okay, so remember that RPM is just rotations per minute. Okay, so that's what RPM is, rotations per minute. So we want to know our angular acceleration, which we just learned is alpha equals to delta V over delta T. Okay, So we can go ahead and plug this in, or we can change these units of our velocity, our angular velocity, to, oh, yeah, this is angular velocity, my bad. This should be omega. Omega. There we go. Okay. So we need to go ahead and change these units. So these units, RPM, okay, rotations per minute, that is going to need to change to radians per second. Okay, so we need to get that rotations per minute into radians per second. Okay, so why don't we go ahead and do that? So our delta omega is going to be 250 rotations per minute. We can start with the easy one first. In 1 minute, we have 60 seconds, right? Okay, so now we're in seconds. Now we need to get from our rotations, how many rotations in a radian, or how many radians in a rotation. Okay, so this is where we would need to think of a circle. Okay, and if I were to go from this angle, let's call it 0, all the way around that circle, how far has it traveled? Okay, so we can say either you traveled 360 degrees, right? Or 2 pi radians. Okay? So whichever one you want to choose, okay? It's the same kind of thing, but we need to somehow get it into radians anyway. So you can go ahead and use this. So 1 rotation for a circle is going to be the same as 2 pi radians. Okay, so let's go ahead and use that. So we have 2 pi radians for 1 rotation. Okay, so what you'll need to do is go ahead and calculate that. Give me 1 second while I get my calculator. Alright, so we have 250 times 2 pi divided by 60, and we get that our delta omega is about 26.2 radians, right, because we converted, per second. Okay, so now this is our delta omega, our angular velocity. Okay, so let's go ahead now and plug this in to determine our angular acceleration. So we have 26.2 radians per second over my time, which is 5 seconds. Okay, and so go ahead and do that in your calculator, and you will get 5.24 radians per second squared. Okay, so this is my angular acceleration here. Oops. Okay. Now, we want to go on to part B. It says, if she now slams on the brakes, causing an angular acceleration of negative 87.3 radians per second, how long does it take the wheel to stop? Okay, so, whoops, part B, we cause an angular acceleration of negative 87 point, whoops, sorry about that, 87.3 radians per second squared. How long does it take for the wheels to stop? So she slammed on the brakes, okay, and we are still going the same speed. So this is my alpha now, okay, but my speed or my angular velocity is still the 26.2 radians per second. Okay, but we want to know how long does it take for her to stop. So we're now going from this omega, okay, to 0. I guess I should put that this is the initial velocity, and my final velocity is 0. Okay, so let's go ahead and manipulate this equation to solve for how long that would take. Okay, so our time would be equal to delta omega over alpha. Okay, and so it's final minus initial, right? That would be our difference. And divided by our alpha, which is negative 87.3 radians per second squared. And so if you plug that into your calculator, let's see, negative 26.2 over negative 87.3. Whoops. Is going to be 0.300 seconds. So it will take her 0.3 seconds to slow to a stop. Okay? For her wheel to slow to a stop. Alright, so that was our first example. Since I don't have much time left, I will go ahead and stop this recording and then continue on with our second example.